So we started a brand new unit. We looked at the physics concept of work. Cooper, I went on a big rant about how work is not tiredness. You do work on something. We said work is calculated by force times distance. Oh, but the force and the distance had to be in the same direction, and the force had to be constant. The units for work were, well, it's force, newtons, distance, meters. It's a Newton meter, but that's such an important concept, we've called that a joule. One of the things that we looked at was the work done in lifting. This is sort of worth memorizing, but it's actually kind of hidden on your formula sheet, so you don't need to panic about memorizing it. The work when you're lifting, we said is mgh. We did a quick free body diagram, and we agreed that the lifting force was the same as mg. Got a latecomer coming in. Looked at a second definition. Oh, one of the nice things about work, it was a scalar. I'll probably go on a rant about that later on, but not right now. What it meant was the path that you took to get to a location was irrelevant. It only cared about what force you did work against. We talked about how a hill, for example, or a ramp is actually what we call a simple machine. You could lift your bike up the back and you would do 12,103 joules of work. You'll do the same amount of work pedaling the bike up the hill, but because the distance got bigger, the force required to pedal up the hill got smaller. We also said that work was the area underneath a force versus distance graph. That's our second definition of work. There's a third definition, which is even better. I think we'll get to it this year. If not, we'll look at it in Physics 12, but now, today. Dina, you ready? Put your phone away. Face down. Annie, you ready? I want to start. We're live. Power. We want to talk today about power. The fancy definition of power worth underlining. Power is the rate at which work is being done. It's how fast you're doing work. By the way, if you're exercising and you're getting tired, it's not because you're doing work. It's because you're generating lots of power. If you want me to ask what causes tiredness, power causes tiredness. If you're getting tired, it's because you're doing the work quickly. You know what? It's the difference between walking up a flight of stairs and running up a flight of stairs. You'll do the same amount of work, but I know which one will leave you huffing and puffing at the end. Okay? What would be a good letter to use as our abbrev for power? Lowercase p is already momentum, so uppercase P is power. And yeah, we're starting now to distinguish between a lowercase and an uppercase. I hope I've mentioned once or twice that we don't have enough letters in the English alphabet. I think I've said that once or twice. Okay, power equals. Ryan, can you read to me the 4 words I underlined? Anytime we talk about the rate, what that really means is you're dividing by time. Power is work over time. And you might want to see where that is on your formula sheet. It should be right next to, I hope, work equals force times distance, or right below it, but I probably would have put it right next to it because they're so related. What are the units? Who remembers what are the units for work? Yeah, you're right. Joules. What are the units for time? You all know this. Power is measured in joules per second. But this concept of power is so important, we've given joules per second a special name. Power is measured in watt? It is measured in watts. Symbol capital W, which is going to lead to some confusion because capital W, when it's on this side of an equal sign, is work. When it's after a number, is watts. When it's after an at symbol, is west. I hopefully have mentioned that we just need more letters in our alphabet. We're having to reuse them. So you'll just have to really keep track of the context of where you're seeing stuff. Power is also a scalar. It has no direction, much like your future. Anyways, it's also a scalar. I like example 1, I like example 1. Example 1 is a nice question. An electric motor is used with a pulley and rope to lift a 650 Newton load from the road up to a height of 12 meters. This job is done in a time of 10 seconds. What is the power output of the motor? Carson, what's this want me to find? Power is work over time. Can you all do me a favor before you go sprinting to your calculator? Can you underline the word lift? That was a trigger phrase in work. Does anybody remember what was the equation for lifting something? How much work done in lifting something? I'm going to give you a hint. It's sort of in disguise on your formula sheet because you're going to find out in a couple of days it's also how you calculate gravitational potential energy. It's 3 letters, yeah. MGH. This is why I said it's worth memorizing, but you kind of don't need to. It's sort of in disguise on your formula sheet. This was the work done in lifting divided by time. What's that 650? What are the units next to that 650, Jordan? What? Davin said convert it. No. Isn't that mg already? Isn't that 650 mg? I could divide by 9.8 to get the mass, but you know what I would do right away? Multiply back by 9. So you can go 650 divided by 9.8, put that in for the m, but I'm going to argue that that 650, that's mg. In fact, if you want to, you can draw a little arrow. That's the weight. That's mg. And this was me trying to do as much review as possible before the final exam, back when we were linear and I had a final exam. Oh, Jordan, what's the height? And the time? 10 seconds. What do you get? $780? Yep. Power is measured in watt? Watts. Okay. The Watt is named after James Watt. To me, he's one of the most overrated people to have a unit named after him, especially such an important unit. All of you have heard of watts because we live in an electric society, and electric power is also measured in watts. How do you get watts for electricity out of mg? We'll talk about how that shows up in physics 12 if you take physics 12. James Watt should not have had a unit named after him, in my humble opinion. There's a second. The imperial unit for power is the horsepower. 1 horsepower is 750 watts. You don't need to memorize that. If I ask you to do a conversion, I'll give you the conversion. So the motor in this example would have a horsepower of, we want to convert 780 watts to horsepower. Who remembers, what was the first thing we always did whenever we were doing a unit conversion? Write down what they gave me. This was me reviewing unit conversion. So I would write down 780 watts. I want watts to cancel. Where do I want it to go in my conversion fraction, Ashton? On the top or on the bottom? So you're saying if I put watts there, that'll cancel the watts out? Ah, and that's the nice thing about this method. It tells you, I guess I'm going to want HP, horsepower, on the top. What's the conversion factor? I guess 1 horsepower is 750 watts. Am I going to times by 750 or divide by 750, Ashton, and how do I know? Why? Because the 750 is on the, the conversion factor method lets you, first of all, double check. You should end up with the correct units being the only ones left behind. And it answers, do I multiply or do I divide? It answers that for you. I'm going to go divided by 750, little more than 1 horsepower. Example 2. A 60-kilogram girl runs up a flight of stairs 3.32 meters high. The stairs in the back corner here are right around 3.3 meters high. I measured them, so you can imagine. Oh, and most of you have a mass plus or minus of around 60 kilograms, so you can put yourself in this place if you want to, in a time of 2.60 seconds. Maya, what does A want me to find? Power is work over time. When you're climbing up a flight of stairs, what you're really doing is you are lifting your body against gravity. Maya, do you happen to remember the equation for work done in lifting something against gravity? Do you need to memorize it, or is it sort of in disguise on your formula sheet? Hopefully you picked up on that hint. Hopefully you have your formula sheet out in front of you by now. So it's going to be mgh over time. By the way, as far as I'm concerned, mght and power, I can give you any four, find the fifth. You can get whichever one you need to by itself, right? But here we're just plugging and chugging. It's going to be 60 times 9.8 times 3.32 divided by 2.6. What do you get? Dina, what'd you get? Sorry? Oh, still typing? 750 decimal 8. Power is measured in watt? Watts. If 1 horsepower equals 750 watts, what's her power output? You know what? Almost exactly 1 horsepower. Really close. And I kind of contrived that on purpose. All of you could run that flight of stairs in 2.6 seconds if you had to. All of you are capable of putting out 1 horsepower for a burst. Now, if I asked you to do that for 25 straight minutes, only the fittest among you could do that. Power is tiredness if we're talking about how it affects the human body. The more power you're generating, the more tired you're going to get. I could probably ask most of you to walk a flight of stairs for 20 straight minutes, and if you went very slowly, you'd be tired, but all of you could do it. But if I asked you to run stairs for 20 minutes, almost none of you could do that, right? The horsepower was originally invented by James Watt. I got to go on my James Watt rant. James Watt, many people will say, I thought he invented the steam engine. If he had invented the steam engine, you know what, Evelyn, he'd be worth having a unit named after. He did not. He improved the steam engine. What he really was a good marketer. When he was trying to market his steam engine to farmers, he made up a unit called the horsepower. And he would say to the farmer, this engine has 3 horsepower. What does the farmer think? This engine does the work of? Yeah, 3 horses. No, it does not. First of all, what kind of horse? You talking a little pony? Talking a big Clydesdale like you see in the Budweiser commercials? Medium horse? There's so much variation. It's a stupid unit, but as marketing, it was brilliant. In fact, it's so brilliant, we still have that stupid unit today. All of our car engines are measured in horsepower. Do any of you have any idea how much work a horse is capable of doing in a given amount of time? No, but we still use it. Dumb. Should be watts, but also shouldn't be named after James Watt. Should be named after somebody else, but I can't change that. If I become dictator of the universe, I think I've told you, I'll redo the calendar, and one of the other things I'll do is the watt will no longer be called the watt. It will be named after some other scientist. Ooh, what are they asking us to find, Jada, in example 3? How long? What variable is that? You know what? I do see power, horsepower, but I see power. I think I'm going to start out by going like this. Power equals work over time. And Jada, I'm going to say, I guess we're going to get the T by itself. Where is the T right now? On the... Bleh. Wait a minute. Dividing by T on the right is the same as doing what with the T on the left? So everybody, if you want to cross out the T on the bottom, you can tuck it here, T times P. What's the P doing? What's power doing to time now? How will I move it over? Here's yet another equation for time. Do you need to memorize it or can you derive it, Jada? I think we can derive it. It's going to be work divided by power. Oh, everybody, please underline the word lift. That's a trigger word. Anderson, what was the equation for work done lifting something? Do you remember? 3 letters. Keep going. 3 letters. Dina, you okay? Okay. Got it? Psst, psst, psst. Look at your formula sheet. Is it hidden somewhere sort of in disguise on your formula sheet? You're also going to find it's the amount of potential energy when you lift something. Okay, so it's kind of there. So it's going to be mgh divided by power. Jada, take us home. Did they give us the mass? Yep. G, 9.8. H, 30. By the way, 500 kilograms, none of you could lift that. So this is something none of you could accomplish. Ooh, why would it be wrong to do that, to put a 10 there? What are the units they gave us for power? We don't do physics with no stinking horsepower. We're going to have to do a conversion. I'm going to do my conversion. I think I got some room right here. So I'm going to start out by writing down what they gave me. I want horsepower to cancel. Jada, where is it going to go in the next fraction? And I want watts on the top, and apparently it's 750 watts. You know what? 10 horsepower is 7,500 watts. That's what's going to go in the bottom here. What do you get? 19.6. It works out nice. That's a fluke. I'll take it, though. Jada, 19.6. Units, time. What if you need it lifted faster? You have to get a bigger motor. It's impossible to get this job done any faster. Now, this is kind of trivial, just lifting a safe up a window. But if you're, for example, designing a large apartment construction, those big, in fact, I think I go on a crane rant. Do I go on a crane rant, Mr. Dueck? Well, we'll see. Let's keep going. Power can also be measured in kilowatts. That's 1,000 watts, or megawatts. You may have heard those terms when they're talking about generators or hydroelectric dams or something like that, because 1 watt is not very large. It's a very, very small unit of power. Example 4, the power of a light bulb, turn the page, is the amount of electrical energy it uses in 1 second. A 40-watt bulb, for example, uses 40 joules of energy in 1 second. What is the power rating of a bulb that consumes 4,200 joules of electrical energy in 70 seconds? Jackson, what's this asking me to find? How about power equals work over time? Work is force times distance. This is a bit of a trick question. Do you see a force or a distance anywhere in this question? No. But what are the units for work? Do you remember? What are the units for work? And this you will want to memorize, but probably by the end of tomorrow. Joules. Did they give me joules in this question? How many joules of energy, how much electrical work have we done in this question? 4,200 joules. Over how much time? How many watts is this light bulb? Yeah, and that's what it means when you put a light bulb in that's 60 watts. What's brighter, a 60-watt light bulb or a 100-watt light bulb? Be obvious. Then what you're really saying is it's going to be converting more electrical energy into light and heat per second than a 60-watt bulb. Also, a 100-watt bulb will be hotter because a lot of the energy goes into heat. A 40-watt bulb, or you know what, a 20-watt bulb, that's what you might use as a night light for a toddler's nursery or a crib or something like that. Doesn't give off much light, a little bit. It doesn't get very hot as well. Okay, so when you're talking about light bulbs, power is how much light and how hot. A microwave is rated at 1.2 kilowatts of power. I'm going to need to do a conversion. Let's cross out the 1.2 kilowatts. Hey, from your green sheet, kilo is 10 to the what? 10 to the 3 or times by 1,000. So 1.2 kilowatts is going to be 1,200 watts of power. You can see I was sneaking in as much unit conversion leading up to the end of the year as I could. It's running for 6 minutes. Nice try, Dueck. We don't do physics with minutes. How do I convert minutes to seconds? It's probably going to be something to do with a 60. So 6 minutes divided by six. Oh, I think times by 60. Okay. Cody, what's this asking me to find? Joules. What do we measure in joules? Starts with letter W. Work. Okay. Power equals work over time. Cody, how would I get the W by itself? I couldn't hear. How would I move the T over? Yeah. Work is power times time. When you start paying your electrical bill, BC Hydro charges you not for power, they charge you for work, for energy in joules. So in this case, it's going to be 1,200 times 360. What do you get? I got 432,000 joules. Yeah. There's a bit of a problem with this in real life. 1 joule is so small. First of all, that's running a microwave for how long? 6 minutes, not that long. You can imagine if you added up your energy bill for an entire month. In fact, BC Hydro charges you every 3 months. If you added up your energy for the 3 month stretch, you'd be in the billions of joules. And people would freak out because they don't know how to interpret numbers that big. And so, what BC Hydro does, in fact, what all power companies do, there's another way to measure energy. It's called the kilowatt hour. Kilowatt power, hour, time. Cody, it's still power times time, like the equation that you generated. A lot of people think because they see the word watts, oh, it must be power. No, it's power times time. You'll get your energy bill when you start paying for electricity on your own in kilowatt hours. 1 kilowatt hour is 3.6 times 10 to the 6th joules. How many kilowatt hours does this microwave use? I guess we want to convert joules to kilowatt hours. When we're doing a conversion, Lauren, what was the first thing that I always told you to do? Write down what they? I want to get rid of joules. Where do I want to put joules in the next fraction? On the, and so it's going to be kilowatt hours, and apparently 1 kilowatt hour is 3.6 times 10 to the 6th joules. Using that microwave oven, how many kilowatt hours would BC Hydro charge you? I guess it's going to be answer button divided by 3.6, scientific notation, 6. Which is a much nicer number. Adults can deal with decimals because they're used to dollars and cents. Units would be kilowatt hours. BC Hydro charges, the rate varies depending on the time of year and the time of day because they want to encourage people to do high power events in the middle of the night when the electric grid isn't being used as much because everybody's got everything shut off. But they basically charge around 11 cents per kilowatt hour. So it would cost you not very much, about a penny to run that microwave. We're pretty good at producing pretty cheap power. Kilowatt hour is a measure of energy, not power. Oh, I saw this. This is from BC Hydro. I was so offended. You know I obsess about units, right? So Calories is the imperial unit measure of energy. Kilowatts is power. This is saying burn energy, not power. Take the stairs. It should say burn energy, not calories, not joules. Take the stairs. Or it should say burn calories, not kilowatt hours. That's a measure of energy. This is just bad physics. That would be like saying, well, the units don't match. Yeah, drive me crazy. You all don't care. I obsess over these things.
Yeah, we noticed. Shut up.
Okay. Take a picture. Did I tweet it? I might have. I can't remember. I might have tweeted it at them. Pardon me? Pardon me? I'm on it to a very, very limited degree. It's become very toxic. I got on it when Canadian astronaut Chris Hadfield was commanding the International Space Station back in, I think it was 2012. He was putting out spectacular stuff on Twitter, and so I started a Twitter account then. But it's really not that pleasant a place, in my humble opinion. Hey, Annie, what's example 6 asking me to find? What's that 40,000? What are the units next to it? No, it's joules. What are the units next to it? The reason I'm doing this, by the way, how many different ways do we have to find time? Like a bunch. So first thing you want to do is plan your attack. I'm clearly not going to be going T equals VF minus VI over A, or any of the, or D equals VI T plus a half AT squared. I think, Annie, I would go like this, right? And get the T by itself. Annie, how do I get the T by itself? Where is the T right now? On the bleh. What would I do first? And then I want to get the T by itself. How would I move the P over? Okay. Time is going to be work energy in joules divided by power. How much energy in joules, how much work does the microwave have to do to cook this thing? 40,000 divided by 800. What do you get? Is it 50 even? Yeah. Units, time. This is how they get the time that they print on the back of microwave oven instructions. So when they tell you how long to microwave it, this is where it comes from. They know how much energy it takes, how much work it takes to cook the object. There's a bit of a problem, though. Microwave ovens come in two main powers. The large ones, like the one that I have over there, that one's rated at 1200 watts. Then there's the smaller ones that are a little more compact. Those are rated at 800 watts. So how long would a large microwave take to cook the hot dog? We did a small microwave of 800 watts. Well, Andy, it's going to be, again, power, no, not power divided by work divided by power. It was 40,000 joules. But this time, your microwave is capable of putting out 1,200 joules per second. What do you get? $33.3? And you may have wondered, but this is why on the back of every single package that has microwave instructions, it always says, note, microwave oven times may vary. It's because they don't know what type of microwave you're using. Are you using one of the larger ones that's typically 1,200 watts, 1,200 joules every second? Or are you using one of the smaller ones, which can only heat things up at 800 joules every second? They don't know. Little nerd trivia for you there. From the page. There's a special version of the power equation if we're moving at constant speed. So can all of you write down power equals work over time? And then Angus, what was work? What times what from your green formula sheet? Force times distance over time. And then if you could all do me a favor, circle the D and the T. Angus, what are the units for distance? What are the units for time? What's meters per second a measure of? I got to be fussy. We're in Scalarville. It's going to be speed, if I'm being technical, not velocity. There is another version of power. It turns out power is also a force times a constant speed. Let me hit pause for a second. This version of power on your formula sheet, I know some years I haven't. Did I also give you that power equals? Yeah, Dina, you're going to leave the phone away. Did I give you force times speed? You know what? On the green sheet? You might want to, next to where it says power equals work over time, you might want to actually make it look like this. So where it says power equals work over time, you also might want to write next to it FV. That might be worth adding to your formula sheet. That might be worth adding to your formula sheet. That might be really worth adding to your formula sheet that you should have had out a long time ago. Okay. Now, when do you use this? It's pretty obvious. They ask for power, but they don't give you a time. Let me give you an example. Example 7a, how much power are you generating if you need a constant force of 32 newtons to overcome air resistance while pedaling your bike at 12 meters per second? Okay, well, first thing I would say to myself is, self, what are they asking me to find here, Evelyn? So I would go like this in my head. I would think, well, it's work over time. Do you see work in joules anywhere? Do you see time in seconds anywhere? And so I would go, okay, I would now move to this one. Did they give you a force? Did they give you a speed? It's not rocket science. Always start with work over time, but then pivot to this one. It's going to be constant force of 32 newtons. What do you get? Times 12. 384. 384? Evelyn, is that what you got? Units, power is measured in watt. If you want to go faster, will that use more power or less power? Well, look at the V. If the V gets bigger, what's going to happen to this answer? And then we get to a stupid Captain Obvious, but here's the physics of why. Hey, does pedaling your bike faster make you more tired or less tired? Be obvious. And it's because power is tiredness and you're generating more power. In fact, it's a double whammy. Not only would the speed get bigger, but air resistance would get bigger. It turns out if you want to go twice as fast, you're going to be generating 4 times as much energy. You're going to be getting tired 4 times quicker. And this is why you may have noticed when you're riding your bike, it's fairly easy without much effort to go from 0 to like medium speed. You can do that quite comfortably. But to go from medium speed to full speed, holy smokes, you're having to work at it. And it's because of that double whammy of air resistance is getting bigger, there's the F, and V is getting bigger. It's really hitting you. So, how could a cyclist go faster but use less power? How could a cyclist go faster but use less power? What else can we change? What's the other variable here? How can we reduce the force of air resistance? We've just explained, if you've watched the Tour de France, we've explained the pose all of the cyclists adopt. In fact, I guarantee, because they're all professionals, every one of them has spent hours in a wind tunnel because everyone's body is slightly different, and they've had an expert watch from the side as smoke passes over them. Okay, you need to drop your right shoulder about 2 millimeters. Okay, you need to bend your knees about a centimeter. Okay, oh, can you drop your head down about a centimeter? There, that's your, and they'll memorize their pose, and that's their most aerodynamic form. They all have that memorized. And so, yeah, how can you go faster? Right? Tuck down. And again, this is something cyclists have figured out, but I always like showing you the physics of Captain Obvious stuff as well. What's your homework? Number 1. By the way, What's the time in this question? Minutes, you'll have to do a conversion. And here's your other hint. The mass, if it's 42 pieces of luggage, each one 24 kilograms, what's the total mass? And you should also underline the word lifts. So it's going to be Anderson MGH, but I think M is going to be 42 times 24. Okay. 2 is good. 4 is good. You can skip 3. Ha 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 ha. 6 is good. I skipped 5. 7 is good. 8 is good. 9 is good. I'm going to skip 10.